Okay, this is Unit 5, Chapter 10, Part 2 of notes. We're going to start off by looking at how we convert moles into grams. Then we're going to look at some multi-step problems that require 2 steps. And then we're going to look at how to convert moles into volume, liters. Yesterday, our first conversion factor was 1 mole equals 6.02 times 10 to the 23rd representative particles. So we had atoms, molecules, ions, formula units. Our second conversion factor is right here. 1 mole equals the GFM, the gram formula mass. So we also call this molar mass, and we actually have to calculate it in order to get the conversion factor. So let's find the mass in grams of 3.32 moles of potassium. We're going to start out with 3.32 moles of K, potassium, and it says find the mass in grams. So to do that, we need the molar mass. So I'm going to look on my periodic table. I look at potassium, it's 39 point, and I'm going to round to the nearest 0.1. So it's 39.1 grams. That's grams of potassium per 1 mole. So we're going to use that as a conversion factor right here. For every 1 mole of potassium, I've got 39.1 grams of potassium. And from here, I can actually calculate, and I can get there. So when I multiply it out, I'm going to round according to 1, 2, 3 significant figures here, and there are 3 here with our molar mass. Final answer, 1.30 times 10 to the second. Because I get 130 when I round, but that only has 2 significant figures, so I had to turn it into scientific notation. Final units, grams of potassium. Find the mass in grams of 15 moles of sulfuric acid, which is H2SO4. First things first, I actually have to find the molar mass in order to convert. So I'm going to set up my problem, 15.0 moles of H2SO4. I need to find molar mass. Hydrogens, I have sulfurs, and I have oxygens. I have 2 hydrogens, 1 sulfur, 4 oxygens. The mass of hydrogen is 1.0. Mass of sulfur, 32.1. Mass of oxygen, 16.0. When you multiply these, 2.0, 32.1, 64.0, and we're going to add these together to get our molar mass. The molar mass here is 98.1 grams of H2SO4 per 1 mole. So I'm going to plug it in. 1 mole of H2SO4 is 98.1 grams of H2SO4. Final answer, I've got 3 significant figures there and 3 here. 1,470 grams of H2SO4. Okay, now we're going to look at a problem that requires a little bit more. It's a 2-step problem. It is a multi-step problem. Calculate the number of molecules, which I'm going to abbreviate MC, present in 4.29 grams of nitrogen dioxide. So, I printed you off a handy conversion chart, and I want you to look at that while we go through these multi-step problems. So if I look at the problem, I'm starting out in grams, and I'm trying to convert into molecules. So that's two conversions. I got to go grams to moles and then moles to molecules. So if you look at your chart, you're starting off down here, 4.29 grams of NO2. And on my chart, I'm trying to find a representative particle, a molecule, way down here. And I'm going to put a question mark there. So the first step is to travel from grams to moles, and then you're going to have to go moles to particles. And I've even listed the conversion factors there. So let's go through it. Number 1, 4.29 grams of NO2. I have to go grams to moles, which requires something called GFM, or molar mass. I'm going to go ahead and give it to you. There are 46.0 grams of NO2. Otherwise, you'd have to calculate it for every 1 mole of NO2. Now, we're going to use the conversion we learned yesterday, RP, representative particles. We learned that for every 1 mole of NO2, we have Avogadro's number, 6.02 times 10 to the 23rd, and I'm going to abbreviate again, molecules of NO2. When we calculate with 3 significant figures, I have 3 everywhere, 5.61 times 10 to the 22nd MC of NO2, molecules of NO2. Okay, second multi-step problem. Calculate the number of moles of sulfur atoms present in 2.1 grams of sodium sulfide. So this one, a little bit more difficult. Let's look at our map. It says calculate the number of moles. So I'm looking for the center, and I'm starting with grams over here in mass. It looks like a one-step problem, but let's check it out. 2.01 grams of Na2S, sodium sulfide. We need the molar mass of Na2S, which I'm going to give to you, 78.1 grams of Na2S. Otherwise, you'd have to calculate it per 1 mole of Na2S. Now, it looks like we're done. But if you read the question carefully, it says calculate the number of moles of sulfur atoms, just sulfur by itself. So here's what I'm going to do. I don't go to particles, but what I am going to look at, I'm looking for moles of sulfur. So in 1 mole of Na2S, I'm looking for how many sulfur atoms are there. There would be 1 mole of sulfur atoms, specifically. We call this a mole-to-mole ratio. When I calculate, final answer, 0.0257 moles of sulfur atoms. Okay, next, calculate the mass in grams of this many carbon dioxide molecules. So we're starting out in particles. We have to go to moles and then mass. (2.49 times 10 to the 20 CO2, I'm going to abbreviate, MC. First step, I have to convert particles into moles. 6.02 times 10 to the 23rd MC carbon dioxide for every 1 mole of carbon dioxide. And then I have to use molar mass. For every 1 mole of CO2, I would have to use the periodic table and calculate to get 44.0 grams of CO2. Final answer when we calculate 1.82 times 10 to the negative 2 grams of CO2. Calculate the grams of carbon dioxide, grams of carbon in 12.2 moles of sucrose, which is a sugar. 12.2 moles of C12H22. Notice it's not glucose, it's sucrose, so the ratio is different. I'm going to go ahead and use a mole-to-mole ratio to get into carbon atoms specifically, because I'm looking for just carbon, not hydrogen or oxygen. For every 1 mole of C12H22O11, how many carbons do I have there? I would have 12 moles of carbon atoms. That's called a mole-to-mole ratio. And then from there, I'm going to use the molar mass. For every 1 mole of carbon, I have 12.0 grams of carbon, and this is the molar mass. So if you look at my chart, I'm starting out in moles, and I'm trying to go to grams. But first, I had to convert into carbon. Final answer, 1.76 times 10 to the third grams of carbon. Awesome. So the two conversion factors that we've discussed below, 1 mole for every 6.02 times 10 to the 23rd RP, representative particles. For every 1 mole, you have, I'm going to call it molar mass. You have to calculate it in grams. So we actually have one more conversion factor to learn, and it's molar volume of a gas. The volume of a gas at 0 degrees Celsius and 1 atmosphere of pressure, which we haven't talked about yet, we call it STP, the standard temperature and the standard pressure. We want you guys to know 0 degrees Celsius and 1 atmosphere. We want you to know that this is the standard temperature and the standard pressure. At STP, 1 mole, specifically of a gas, I want you to circle that, has a volume of 22.4 liters. We call it molar volume of a gas, and it contains 6.02 times 10 to the 23rd particles. So this is going to be our third conversion factor. 1 mole is 22.4 liters, which also equals that many particles, which equals the molar mass. They're all connected. So our last and third conversion factor, 1 mole of any gas is 22.4 liters. So let's calculate. What is the volume at STP of 0.960 moles of CH4? Well, here's the conversion. For every 1 mole of this gas, CH4, we have 22.4 liters. Final answer, 21.5 liters of CH4. Very straightforward problem. Next one, at STP, how many moles are in this many milliliters? So here, I'm going to start out with 0.542 milliliters of neon, but my conversion uses liters, so I'm going to go ahead and convert. For every 1,000 milliliters of neon, I have 1 liter of neon. 22.4 liters of neon for every 1 mole. There's my molar conversion. Final answer, 2.42 times 10 to the negative 5 moles of neon.